All right. So basically when let's briefly review the procedure. So if I'm solving I'm in a tube and I'm solving for a velocity and the distribution and pressure. So first things first, you set up your coordinate system so it's aligned with the tube walls. That way you will have the chance of having some of the velocities being zero and only maybe one having non-zero, because that allows us to solve ahead, right? So there's nothing wrong with using the Cartesian coordinate system here, but Vx, Vy, Vz would all depend on x, y, z. And then that's called, well, you better have numerical solutions already in the simulator that can actually figure that out. Without that, basically the best approach is to align the coordinate system with solid walls. And in this case, that's a cylindrical coordinate system. So in the center of the tube, so boundary conditions on the tube wall, most common ones, that help us solve the equation later, are no slip, which means that basically your velocity moves with the wall. In this case, wall is static, so that velocity is zero. So all of the components of velocity are zero, but what we're really using in this one is we're looking for VR, so we're saying, okay, VR is zero on the wall. Okay? In normal situation, when I would have other velocity components that I'm looking for, I'm not looking for V theta and Vz here because I'm assuming they're zero. They would be zero on the wall as well. Okay? So that's what no slip means in most general case. Now, what we were getting there, so basically what I do is a shell balance. Now my shell is this cylindrical, like annulus. Okay? Annulus, it goes from R to R plus some small delta R. And it has a thickness Z. So it goes from some coordinates Z to Z plus delta Z. And we balance momentum, what's coming in and out, through these boundaries on that shell. And then I shrink it in volume. So I take those delta R and delta Z to go to zero, and that gives me a differential equation for every point. Okay? That's the general idea. Now I have to have my phi, which is combining all of the components of momentum and momentum or stress transfer everywhere. So I have the hydrostatic component, which is the pressure one. I have the viscous component, that is the tau. That's a viscous stress tensor. And I have the convective one. That's the rho VV. Okay? So now they're just going to be in the cylindrical coordinate system. So if I'm looking for Vz, I'm going to balance Z momentum first. And once I find Vz, the others I assume they're zero, so I'm going to be solving for them. But if I were, I would guess that they're zero. Okay? So essentially, I might phi ZZ is Z momentum transfer across the Z plane. So I'm going to use somebody's, if you don't mind. So this is my Z plane. These are two Z planes, right? And my R planes are curved. Okay? So my R planes are cylinders, and basically my phi ZZ is Z momentum transfer across Z plane, and I have it at Z plus delta Z. And I have phi RZ, which is Z momentum transfer across R plane, and that's across R. So basically I have the inside part of this annulus and the outside part of the annulus. And the key thing here is that those two annuli are of different area. And the outside one is a little larger. So basically, as I'm moving away from the center of my coordinate system, my R planes have sort of like, even in the small shells, they have larger and larger area. And I have to make up for that, and that basically shows up in the equation. I'm not going to go through the derivation of the entire equation again, but basically that's why I have 1 over R here, and I also have R times PRZ, because it's R times PRZ that is constant. Okay, so PRZ, which is divided by area, and that area getting larger and larger as I go away from the center. PRZ is getting smaller and smaller away from the center, and what's conserved is R times PRZ. Yes? That's because of the changing areas. In Cartesian coordinate system, I don't have changing areas. So the equation will look slightly different. Be attuned to that Cartesian coordinate system and cylindrical coordinate system do not have completely equivalent forms. Sometimes they do, but often I have to make up for this curve and this changing area as I'm changing R. So this equation is general. Okay? So I have phi z, z, so basically for z momentum balance in a cylindrical coordinate system, this is general. This part rho g is not very general, but technically as long as I look at g as gz, z component of gravity, then this will be general as well. Okay? And for, I have to also say that there's an effect here. Well, it's a plus gz and my so here I have an assumption that my z is pointing downwards, right? So my gz is plus g. Okay? If it was going upwards, it would be minus g. So just be sensitive. As long as if I change this to gz, this would be very general. And I could apply it in a horizontal case or an inclined case as long as I calculate what my z component is in the coordinate system that I'm thinking about. Okay? So that's something to bear in mind. And we are going to actually use it. Now, after this, we have not actually even applied any assumption about the fluid yet, other than constant density rho. So basically, this could be vapor fluid, this could be parallel fluid, it could be anything. It's now that I'm going to write down what phi is that I'm going to assume Newtonian fluid. And that's going to be important for today's example. So when I do that, basically I write down what phi zz is with all of the components, what phi rz is with all of the components, I put them in. A lot of things go to 0 because either the velocity component that I'm looking at is 0 or the derivative with respect to a coordinate of a velocity component is 0. So Vz is not 0, but Vz is 0 because I don't have dependence on z. Okay? So things cancel out, and here I get derivation of the, so I get that basically this is my equation when I write it down. And then to actually solve this, I notice that one portion of it depends on R, and the other portion, so my pressure changes in Z, and my velocity changes in R. Okay? For those two functions to be equal, they essentially have to be constant. It cannot depend either on R or Z because I wouldn't have them be equal. Okay? So this is sort of almost like a mathematical trick of sorts, so you have to look for it. So to be equal, they have to be equal to a constant. And then I basically assume that this is a constant and solve them separately. And I will get pressure. So dP dz is constant. I get a linear function for pressure. And here, if this is constant, then I have to go and solve the equation. In solving the equation, I get that tau rz of R is minus PL minus P0 over L, R over 2, plus some constant E over R. This is where I now need boundary conditions to solve this. Normal boundary conditions for tau RZ, or for shear stress in general, is continuity on some boundary. That's one of it. So when we had a thin film down the slope, I had a continuity which is on the boundary of liquid and air, which effectively meant that tau, what was it, xz in that coordinate system is equal to 0, because viscosity of air is so low that my shear stress is 0. Okay, so that is effectively continuity on the boundary of air and liquid. Okay? In this case, I have exposure to the solid. I don't effectively have exposure to any other liquid. And I don't know what tau RZ of the solid is. I don't have that information. But I actually know that in the middle of this geometry, I shouldn't have this one for R is equal to 0, which is effectively in the middle of my geometry. This should not blow up. I cannot have a nice Newtonian fluid like water in laminar flow and shear stress tensor blow up. That just makes no physical sense. Okay? Therefore, this has to be 0. Now imagine, so, okay, I assume it's 0 and I get this linear. One bill. Okay. So some of the boundary, this is essentially not a boundary condition, but it's a bounding condition. I cannot have things blow up in my geometry. Okay, for normal fluids that we're dealing with. Yeah? Okay. So that's sort of, let's call this one a common sense condition. It's not a boundary, it's in the middle of the geometry. Now, what if this was an annulus? Would I have that apply?
If it was an annulus? No.
Yeah, because the center of the tube is not inside of the annulus. Okay, so you have to be careful with that. In annulus, it doesn't matter, it's outside of the geometry. So I can have plus E over R, and technically then I don't have a boundary condition on shear stress. I gotta go to velocity distributions to figure out what E is. Yes?
In an annulus, wouldn't it also be different because like the center is solid too, or wouldn't the center be solid?
So my shell, that's a great question. So my shell, if I'm solving in an annulus and not an entire tube, this entire derivation is actually the same. I'm a cylindrical geometry aligned with my annulus. And the shell is the same as long as it's within my annulus. Okay? It's the boundary conditions that differ. So then I will have a boundary, and that's actually one of your homework examples, the last one I believe for Wednesday. Did you get to? Smile. Okay, so in the middle, so basically I have this two solid boundaries. Okay? And it's those two solid boundaries, I will have no slip condition on both of those solid boundaries. And those are going to be my boundary conditions. So boundary conditions, they change depending on the situation. But then basically, in that situation, I cannot say E is 0. If you have an annulus, so again, that's your last homework problem. You cannot assume this is 0. You just take it, it's E, or whatever you want to call it. I'm calling them C, D, E, F. Call them C1, C2, whatever you call them. Just they're constants, and you need to find them. So essentially, you would carry this, and you would go into velocity distributions, and you have two boundary conditions for velocity, inner and outer wall. Okay? And you have no slip on those boundaries, and I believe in that homework example, the inner one is moving. Okay? So the boundary condition is the velocity of that moving solid. Okay? So your dz is set to the moving piece of machinery. Yes? Okay. So no slip means moving with the solid boundary, whatever that movement might be or not. Might be static. Questions? So this is, I would call this the common sense condition in case your R is equal to 0 is actually inside of your geometry. And in those cases, you will get that shear stress is sort of it's a linear function of R. Okay? So it's maximum on the solid boundaries, and it's minimum where R is equal to 0. Okay? All right. So this particular differential equation was general. Okay. I can see that this is a cylindrical in the curved coordinate condition, not a curved coordinate system, not just because I'm using R, but also because I have this 1 over R basis. Okay. That also tells me it's a curved condition. And I'm missing R here. VRZ times R. Okay, plus rho G, apologies. And again, what I wanted to comment on is this is generally taken as G is GZ, so Z coordinate of gravity, which in this case is equal to gravity. Okay. Now, if I had a horizontal tube, this would be 0, for instance. Because a horizontal tube, I would not have effective gravity. And my Z would be in line with that horizontal direction. Yes? Okay. Now, let's actually solve this, our last example in this case. So these are in that video that is hard to hear. But I essentially have gone over boundary conditions in this by reviewing 1 and 2. So I want to now move to Bingham plastic. And let's just recall that Bingham plastic sort of remains rigid or doesn't move until I have enough stress applied to it. And I'm calling that stress yield stress tau 0. And then after that, I have this sort of shifted behavior. It's like same as the Newtonian, just shifted by yield stress. So my tau yx is minus mu 0 dvx dy if that shear stress is larger than yield stress. Otherwise, I don't have a proper relationship between shear stress and the velocity distribution, because technically in this region I'm not a fluid. And I'm actually a piece of solid. And I'm moving by inertia along with whatever is my fluid boundary. Okay? And that's basically expressed that, well, my Vx is whatever, dvx dy is a 0. So I'm a constant, whatever is my boundary moving with, that's what I'm moving with. Okay? That's essentially expressing inertia, and I have now solid behavior. So I have part solid, part liquid behavior, mathematically expressed this way. I'm just going to play this short video. I played that already, but just to give you a little bit of intuition for the Bingham
bottom, and this vessel is open to the atmosphere on top, and yet this clay suspension does not flow. I can put this simple piston here, place this small weight on it, still no flow. Now a larger weight. It flows, but very slowly.
So I'm above that field stress.
A much larger weight. The flow is fairly rapid. I take the weight off. The flow stops. In a state of equilibrium, this material can support a shearing stress up to a critical value called a yield value. Even with materials not having yield values, the Newtonian fluid cannot explain many flow phenomena.
Okay, so this is just to remind you of how Bingham plastic looks like. And now I'm basically gonna switch to writing. Let me just insert myself a couple of slides. And we're going to solve for Bingham plastic or fluid in horizontal tube. There we go. Okay. A little bit of lag always when I have multiple things attached. Okay, so our new example, and it seems that my default color is red, is Bentham plastic in horizontal tube. And I'm still going to assume steady state laminar flow. And I will assume constant density fluid. Whoops. Constant density flow. So those are my assumptions. Let's draw the geometry. It's horizontal, so I'm going to draw it that way. Still going to assume radius r. And my cylindrical coordinate system will now be horizontal together with the tube. And this is still of length L. And I have P0 and PL, so I have a pressure difference driving the flow. I'm not going to rederive Z momentum balance, okay? We have still an assumption that only my VZ velocity is non-zero because I have this pressure difference in Z direction that is driving the flow. Obviously, I can have pressure differences only in Z direction, so my pressure depends on Z, and only my VZ is non-zero, okay? So VZ is a function of R. I don't have anything driving the flow radially, right? So I'm going to assume that VR is zero, and nothing is rotating, so my V theta is zero. And my pressure is a function of Z. So those are pretty much same assumptions as my flow of Newtonian fluid, which was in vertical tube. So I would do Z momentum balance. The way I derived it, and I pointed it out in the review, was pretty general at the beginning. So I'm going to keep that part that I can borrow from the derivation before. So Z momentum balance gives differential equation. I'm just writing dE, which is minus phi ZZ dZ minus 1 over R ddr of R phi RZ is equal to 0. What did I omit? Gravity, because gravity in this coordinate system, the Z component of gravity is 0, right? So note, I'm going to write that note so you have it. Oh, okay, come on. Note, and why didn't you change the bar? Note, GZ is 0 in this coordinate system. So that I don't have the action of external forces, or gravity cannot change my momentum. What's driving the flow is just the pressure difference applied. So just like before, I'm going to put the dot just like before. I will have that 1 over R ddr of R tau RZ is equal to minus, we have that generalized pressure dPdZ. Well, here I don't have gravity, so the generalized pressure is the same as the thermodynamic pressure, okay? So, note, Gz is 0, so my generalized pressure is the same as pressure from previous derivation. And this generalized P is what I call the flow potential. So I had the thermodynamic pressure P minus rho Gz. Okay. So my tau RZ is, and now that I could basically write dPdZ as PL minus P0 divided by L. Quite frankly, dPdZ is simply shorter to write. So I'm just going to use dPdZ. Okay? So I'm going to put this note here. And this, whoop, and then I somehow erased it. Great. So this is equal to PL minus P0 divided by L. Because it has to be constant, and that constant is basically the difference in endpoints divided by L. But I'm going to use dPdZ simply because it's shorter. But I know it's linear function, and this is the slope. Okay, cool. Before I move on, is this all of this clear, or am I going too fast? Are we good?
Is that, you accounted for the negative, right? So you just like...
Oh, this would be negative.
Oh,
Okay, negative this. If I accounted for the negative, it would be P0 minus PL over L. I like thinking this way better because this is PL minus 0 over L minus 0, and that's the derivative in a discretized way, right? So when I see dPdZ, that's what I write. But I always have a minus because when all the coordinate systems, they point from smaller coordinate values to larger coordinate values. However, I flow from larger pressure to smaller pressure. And that's essentially how this minus shows up in derivations. Right? So I kind of flow counter what the coordinate system would point. Anyway, so my tau RZ is minus dPdZ times R over 2. That's what we called E over R. Yes? Then I divide by R and integrate. And E is constant. Now this is Bankham fluid, but it's still within my geometry, and I'm in the coordinate system. So I will use the same argument. So I'm going to call it common sense condition that says tau RZ should be finite at the center of the tube. Therefore, E is 0. So technically, my tau RZ looks the same as for Newtonian fluid. Okay? So momentum the shear stress itself looks the same as the 4 Newtonian fluid. It's how fluid responds in terms of how the velocity distributions adjust themselves that differs between the two fluids. Is that clear? Okay. So shear stress itself is the same, but what fluid does in response and what type of resistance it has to that shear stress is what differs between Bingham fluid and Newtonian fluid and power law fluid or whatever other. Okay? So this is linear, same as for Newtonian. It's just that in our vertical tube, our dPdZ looked a little different because it had that gravity or hydrostatic component. But overall, if I'm just thinking about dPdZ as a driving potential, this form is the same in both fluids. If I had a horizontal tube and Newtonian fluid, this would be the same. Questions? Okay. Now this is where differences kick in. All right. So now I have to basically figure out, I have that relationship between tau, we had tau yx, tau rz would look the same in this case. So my tau rz is minus mu 0, what we refer to as mu 0, dVzdr in this case, plus some yield stress tau 0. So now I have a yield stress. And I know that whether I actually apply that formula for Bingham plastic depends whether I have shear stress that is large enough. Well, I don't know that. Also, my shear stress, it changes. It goes from 0 in the middle to some maximum value on the solid boundary. Like, it's a linear function, right? I just got that my shear stress is a linear function, and that linear function goes from 0 in the middle of the tube, and some maximum, in absolute sense, it could be positive or negative, that really doesn't matter. But in absolute sense, it has some maximum value on the boundary. So it's a linear function, somewhere in between, I'm going to hit, hopefully, that tau 0. But if I don't, I'm not flowing. And if I do that somewhere in between. But I don't know where is that necessarily happening. And this is a little bit of a tweak of how to solve for this mathematically, depends in which region I am. Is that clear? Okay, so let's do that then. Question is, so let me first note, once again, and in writing. So tau RZ changes linearly from 0 to some maximum in absolute sense. It could be very negative and minimum, right? In absolute sense, value on R is equal to R, right? If that maximum is less than tau 0, I'm done. I have nothing to solve for, nothing's flowing. Okay? However, so if that tau RZ max is less than tau 0, we're done. Vz is equal to 0 everywhere. No flow. But I can change that because if I crank up the driving pressure, okay, I will hit that tau 0 eventually. Otherwise, tau R0 at some R0 is equal to tau 0 for some R0 in 0 to R. So somewhere inside my tube. And then I have two regions. There's one region where my shear stress, tau RZ, is changing from 0 to that value, tau RZ, tau 0, right? So I have regions 0 to R0 and R0 to R. Anybody following me? I have some strange feedback from the room coming. No? Is this clear? No. Okay, let's go again. So I have a tube. Okay. So now if I'm just looking at R direction, right? And I'm plotting, I'm going to plot it in this downward direction too. Tau RZ. Okay. Tau RZ is going from 0 in the middle of the tube because tau RZ is minus dp dz, which is some constant times r over 2. Do we agree? Okay. And that constant is essentially minus PL minus P0 divided by L, R over 2. So I have a full description of tau RZ. Okay. So it's changing from 0 in the middle to some value, okay? This is my R, to some value here. Okay. This is my plot of my tau RZ versus R. I'm just pointing everything downwards. And this is my tau RZ of R, which, by the way, tau RZ of R is minus PL minus P0 over L R over 2. Yes? So I have R, uppercase R. I'm the person in the lab cranking up pressure, so hopefully I'm measuring, if anything I'm ever measuring, I'm measuring pressure. If I don't, I have nothing to work with in petroleum engineering or otherwise. Okay? So I have what my tau RZ is. Okay? Now, if, again, this value is less than tau 0, we can go home, we're done. But most likely, I'm actually hitting tau 0 somewhere here, somewhere in between. Yes? And if I'm not, I'm done, but then I have nothing to work with. Okay? So I'm assuming R0 is, I don't know where that is, but I'm hitting it somewhere. Yes?
Is the original one, it was a Newtonian? And then like,
the shear stress looks the same for Newtonian and Bingham.
okay.
I'm just now trying to get to the velocity distribution, and for that I have to know where is my yield stress. Okay? For Newtonian, yield stress is 0. Okay? Or rather, I don't have it, I'm flowing. If I have applied pressure difference, I'm flowing. Here I'm saying that there is a critical applied pressure difference, okay, that makes this flow. Okay? So this essentially has to be larger than tau 0. Yes? So this, you basically have to flow for any portion of Bingham plastic to flow, I should have minus PL minus P0 over L, which is my minus dP dz, if you'd like, however you want to think about it, has to be larger than tau 0 times 2 over R. Do we agree? That's just from this. It's from here, right? So that is my critical pressure difference for anything to flow. And in that case, I have the situation where portion of this is the part, okay? This is where my tau RZ is less than tau 0 in absolute sense. And this is the part where my tau RZ in absolute sense is larger than tau 0. And I'm drawing it as positive, but again, it could be positive or negative. That somewhat depends on how I'm orienting my coordinate system. Yep. Okay. So now we actually have to, I solved for shear stress. That part was easy. Question is, what is my velocity distribution in response? So basically, let's look at this region where my tau RZ is larger than tau 0. So when, or where, rather, tau RZ is larger than tau 0, I know that my tau RZ is given as minus mu 0 dVz dr plus tau 0. That was my description of Bingham plastic. And the only thing that I flipped on you is that the way we defined it in introductory lecture, we said tau yx is minus mu 0 dvx dy, right? And here I changed those to cylindrical coordinates. Okay, so great. I know what this says, right? This is equal to my dp dz r over 2. So my dvz dr is, when I divide by minus mu 0, I get 1 over 2 mu 0 dp dz r plus, this is minus tau 0 over tau 0 over mu 0. So my dz of r is equal to 1 over 2 mu 0 dp dz r squared over 2 when I integrate, plus tau 0 over mu 0 r, oh, okay, plus, what do you want to call the constant? C, E, D, H. There we go, H. How do I get H? I need a boundary condition to get H. What boundary condition can I apply? This is the portion where, by the way, R is larger than R0, so I'm in R0 to R region, right, for R. Yes?
Did you forget R?
Yes, I did. That was a test. So what boundary condition? I'm close to the solid boundary, hint, hint. No slip. So is the boundary moving? No. So what is my VZ of R? 0. No slip. BC. And when I put that in, my H is basically negative expression with R is equal to uppercase R of this, right? when I set that to 0. So my h is minus dp dz minus r. And that gives me, I'm not going to rewrite it, that gives me velocity distribution. But that's just in this part that is moving. Okay? When or where tau rz is less than tau 0, which is basically for r in 0r0, mathematically speaking. Shear stress we know, but it doesn't help us to find velocity distribution because it's not larger than yield stress. So the only thing we know in that region, what we said in the description of the fluid, is that dBz, dr is 0. And technically not related to shear stress. Technically not related to shear stress. Because shear stress is too small to matter. So I just need one more minute to wrap this up. So then my Vz, based when I integrate this, Vz of I in this region is constant. Since we started with H, should we call this G constant? And I need the boundary condition to solve that too. What's going to be the boundary condition? That's essentially continuity between those two regions. So it has to be, so Vz of R0 has to match the above formula when evaluated at R0. So basically, this entire big expression just evaluated at R0. I'm going to be lazy and not rewrite it. Okay? So that's continuity of velocity. And I somehow magically touch. Yep. So there's nothing new that I introduced except that this is just like mathematical dance between different regions because of my description of Bingham plastic. Yes? All right. I see you on Wednesday. And speaking of continuity, we're going to cover equation of continuity. Fancy name for mass balance.